Hi everyone, my name is Nanjiang. I'm a PhD student from the University of Nebraska-Lincoln. Today I'm going to talk about how do we reduce the power consumption of immersive video streaming. This paper is a collaboration work with all these great researchers from both academia and the industry. Now let's begin. As we know from the title of the paper that we will talk about immersive video streaming, which is also called VR video streaming. And in this paper, we will focus on the smartphone-based HMD because they are wireless, they are more affordable and more easy to operate, which makes them one of the most popular choices in the market. And typically, HMD will download all the video content and all necessary libraries from the cloud servers through the network. And inside the HMD, the software will process the video frame and the hardware will record the user's head's orientation. Then the whole system will generate the view for the users, and every time the users switch their views, the view will be updated so that they will feel like they were inside the video. But this kind of special user's experience does not come for free. Just like many other applications on the smartphones, immersive video streaming is also a very high power consuming one. And on the other hand, the existing technology limits the battery life on the smartphones. And moreover, and for the smartphone-based HMD, since they are wireless, we are not able to charge the system while they are being used. Therefore, in this paper, our goal is to find a way to reduce the power consumption of the system. But before we do that, we need to figure out what exactly drains the battery in the system. Based on our previous published work on NOSDEV 2017, we did the power breakdown analysis, and we first come up with these 5 power components that we think are important in the system. And since we cannot directly measure the power of each component, we also designed these 5 test cases. And by doing the power differential analysis, we can find out the power consumption of each component. For example, if we take the power consumption of case 1 from case 2, we can find out the power consumed to keep the screen turned on, which is the display component here. And by doing that, we finally come up with this pie chart, which tells us the percentage of each component from the system in terms of power. And we can see here, the video generation is the most power consuming component from the system. So many work has been done for the 2D video streaming system in terms of power optimization in both mobile system and multimedia community, but very few work has been done for the immersive video. And there is some work trying to reduce the power consumption of the display component. And as for the video generation component, one solution is to build an edge-based system which offload the computation task to the edge server. And the other solution is to build a hardware-based system which adopts something like FPGA to reduce the power consumption. And in this paper, we want to solve the problem from the software aspect to bring the minimum modification to the system. So this brings us to the first challenge, which is how do we reduce the power consumption of the video generation from the software aspect. So before we do that, let's take a look at how the video is generated for the users. So we have a 10 seconds immersive video frame here in the rectangular view, which is one of the most popular presentations of the immersive video frame. And if we assume this is the view of the users, then in these 10 seconds, let's see, we have this first and last user's view, and typically the system will render each pixel of the user's view at a frequency of 60 times per second, and which means the frame rate is 60 FPS, and that makes the total number of view generation 600 times in these 10 seconds. And based on this observation, we come up with the idea that if we want to reduce the power consumed in the view generation, can we reduce the times of the video is generated in a certain time? In another word, can we reduce the frame rate? Well, if we look at the same 10 seconds immersive video, instead of 60 FPS, what if we reduce the frame rate to 30 FPS, and that will make the total number of view generation to 300 times? Will this help save the power for the system? Well, our preliminary test indicates a very obvious power reduction when we reduce the frame rate. However, this brings us another challenge, which is the video quality. So we know that it's not just in the immersive video streaming, but in any other multimedia streaming system. The quality of experience is a very important thing to the users. In our case, it's very obvious that the frame rate reduction will reduce the QoE for the users, and this is something that we don't want to do. So that we have to find a way to save the power without bringing any noticeable QoE reduction to the users. And before I talk about our solution, let's take a small example. So this is a recording of me watching a short immersive video. You can see when I quickly switch my view from my front to my back, I kind of didn't see the statue to my right. Actually, it was ignored by me. So based on this observation, we draw two conclusions. And the first one is we cannot see things clearly when we switching our view very fast. And the second thing is we actually do not care about what we will look at while the view is quickly switched from one point to another. And based on those two conclusions, we come up with two rules that we will follow where we reduce the frame rate. The first one is we do not reduce the frame rate at all where the view is fixed. And the second one is we only reduce the frame rate where the view is quickly switched. And how much we reduce the frame rate is depend on the velocity of the view switching and the video content. We also find some biology research to support our idea. Basically, this sentence tells us we cannot see things clearly when we're moving fast. This also supports our observation and conclusion from last slide. So given these two rules, we proposed our final solution and we name it QuRate. Let's see, we have our original system here, and when we introduce QuRate, we first adopt the dataset of some previous users and videos and generate the frame rate library. Then the QuRate will also take the user's movement data and calculate the velocity of view switching in a certain time period. And then based on this velocity, QuRate will find the corresponding frame rate from the frame rate library and assign those frame rate value back to the original system, so that the HMD will generate the views for the users in the assigned frame rate value in a certain time. So before I talk about the detail of the frame rate library, let's take a look at how we evaluate the video quality. In this paper, we adopted the STV-QM matrix to evaluate the video because it considers the video motion of both video content and the user's view switching. And the STV-QM is a function of the TISI information and the frame rate, where the TISI stands for temporal and spatial information of the video content. And if we reverse the formula, we will find the frame rate based on the TISI information and the STV-QM score. And in practice, the TISI can be represented by the velocity of the view switching v. So if we further rewrite the formula, we can find the frame rate as a function of velocity and the video quality q. Now let's take a close look at the frame rate library. First, we will adopt some users' movement data and the video content from the cloud server and retrieve those users' view from those data. And then we calculate the velocity, the QoE score, and the frame rate as I just introduced. And then we will come up with this frame rate library. And then we will insert the frame rate library back to the source code of the immersive video player. So every time a new user comes in, we first set a QoE threshold, which tells the software the lowest QoE score we will allow in this streaming. And then, based on the QoE threshold and the velocity of the view switching in a certain time slot, we find the best frame rate to the user so that we can reduce the power consumption without bringing any noticeable QoE reduction. So we build an end-to-end system to evaluate our QuRate. This is the power measurement system setup, and we also adopt 5 smartphones in our experiment. We try to cover different brands and different types of settings of the smartphones, and these are the 6 videos that we adopt from this dataset paper, along with 21 users' head movement data. In order to better evaluate our QuRate, we also designed 3 test groups. The first group is default, which means we do nothing to the system. The second group is naive, where we always reduce the frame rate to 10 FPS, which is the lowest frame rate that still ensure a smooth playback in our system. And the third group is the QuRate, which is our solution. In the power comparison, we can see that QuRate always consumes much less power than the default group, but it's higher than the naive group for sure. However, when we look at the video quality, we can see that QuRate is always much higher than the naive group, but it's not necessarily lower than the default group, which means the impact of the QuRate to the QoE is very minor in the experiment. So for more experiment result and the conclusion, please take a look at our paper. We also conduct a battery stress test where we continuously play the immersive videos on the smartphones and drain the battery from 100% to 0%. And our result indicates 70 to 124% battery life extension. So that concludes my talk today. So in this paper, we first conduct the power measurement of immersive video streaming and identify the video generation as the most power-consuming component. Then we propose the QuRate, the QoE-aware and user-centric frame rate reduction for power saving. And our experiment indicates 5 to 32% power savings depending on the user's head movements. We also open sourced our code to the community and received the reproducibility badge from the ACM. And this work is sponsored by National Science Foundation. Thank you for your time, and if you have more questions, please feel free to send us emails or join our Q&A sessions during the conference. Thank you, and stay safe.